Hello, everyone. Welcome to the April 21st edition of Math 336, Math Stats. I want to let you know that your last homework for the semester will be due on Monday, the Monday before reading day. So today we're going to learn about the chi-square test for homogeneity. Now, this is the test where we see whether two populations follow the same distribution or not. For example, you could be a manufacturer creating steel bars, and you want to know how much stress can the steel bar go before it breaks. And you might want to know, does the distribution from the old method of producing the steel bars produce the same distribution as the new one? That's something that you will want to know. Now, this test requires us to learn a little bit of theory, but you will see how we revert back to things we've learned before about the chi-square distribution and different principles we learned that affect the number of degrees of freedom of a chi-square distribution. So we're going to start off talking about the theory. And you might be wondering, okay, why do we talk about the theory every single time before we do a test? Well, the reason we always talk about the theory behind the test is because it's very difficult to remember what kind of test should I run if you don't know why the test works. You guys aren't computers. The computers can remember this stuff way better than you can. And so the task that we're training you for is to be able to understand why do certain tests work, and then it will be far easier to remember when to use them. Lastly, for those of you who need some kind of external motivation, this kind of stuff comes up on various actuarial exams. All right, so let's begin. So we have two experiments, and they're independent. Independent experiments. And they can end up in one of k mutually exclusive outcomes. We call those outcomes A1 through AK. So we say that Pij is the probability of landing in that outcome for I equals 1 to k and j equals 1 or 2. So let me kind of specify a little bit more. What we're saying here is P11, P21 up to PK1. These are the probabilities of A1 through AK in the first experiment. And these probabilities are the probabilities of A1 through AK occurring in experiment 2. Okay, so what should be clear is that these probabilities add up to 1, and these probabilities add up to 1. So we notice that we have two subscripts for each probability. So we do the experiment, and we perform N1 trials in experiment 1, or from population 1. And we do N2 trials in experiment 2. And they are independent of each other. So there's a lot of notation for this, so you'll slowly get it. Y1, 1, Y2, 1, YK1 are the frequencies of these certain outcomes in the first experiment. And y12, y22, up to yk2 are the frequencies of these outcomes in the second experiment. So what's basically happening? Let's give you kind of a possibility. We have a dice, and we have another dice, and these dice are possibly loaded. And the first dice you roll a bunch of times, and you can get numbers 1 through 6. The second dice you roll a bunch of times, you get numbers 1 through 6. And then y11 will be, okay, how many times did I get a 1 on the first dice? Y21 will be, what's the number of times I got 2 on the second dice, etc. And then y12 on the right here is the number of times I got a 1 on the second dice. Y22 is the number of times I got a 2 on the second dice. And that's a good way to think about this. So what we notice is that y11 plus y21 plus yk1 should equal n1. That's the number of times we've rolled dice 1, so to speak. And y12 plus y22 plus yk2 should equal n2. That's the number of times we rolled dice 2. So what we know is that this sum right here this is approximately chi-square with k minus 1 degrees of freedom. That's for, you could do the first experiment or the second. And we know this from our discussion in section 1 of this chapter 9, because basically we're looking at the observed outcomes minus the expected squared over the expected. That's the way these chi-square variables always work. So what happens when I add them? So let's look at so we have a double summation. I think I messed up there a little bit. There we go. If we add this up, we see that we have this is chi-square with k minus 1 degrees of freedom. This is chi-square with k minus 1 degrees of freedom. So that means that this new distribution, when we add them, assuming independence, is approximately chi-square with k minus 1 plus k minus 1 degrees of freedom, which is chi-square with 2k minus 2 degrees of freedom. So what was the assumption here? Well, this setup is perfect for a hypothesis test where we want to test, are these probabilities all the same? That is the probability of rolling a 1 on the 2 dice the same? Is the probability of rolling a 2 on the 2 dice the same? And the probability of 3 on the 3 dice the same? Unfortunately, you don't know, in a more general situation, you don't know any of these. Yeah, you don't know your dice probabilities, and you wouldn't even want to guess them in advance because you suspect that they're weighted. Now you might do a hypothesis test to say, okay, is the probability of each dice 1/6? You know, that you can do, but you wouldn't be able to know that they're the same if they're weighted. So what do we do? Well, we need to estimate. We need to estimate this probability using the relative frequency, or the total relative frequency, yi1 plus yi2 over n1 plus n2. You see, if you look at this top, if you look at the numerator, this is the number of times that you saw an outcome in AI. That is, what's the number of times total you saw a dice roll in an eye showing. And this is the total number of trials. So if you're working under the assumptions of the null hypothesis, you would estimate what these probabilities are by just looking at the relative frequency. So this is essentially the total relative frequency. Of AI. All right, so one remark is we only need to do this for P11, which we're assuming is equal to P12, P22, which we're assuming is equal, sorry, P21, which we're assuming is equal to P22, up to Pk minus 1, 1 equals Pk minus 1, 2. We don't need to do it for Pk1 and Pk2 because it's determined by the others. So we're going to substitute this in. So we're going to substitute this in for Pi1 and Pi2 in our equation for our chi-square variable. And we're going to get a relatively nasty looking expression. And that is our new variable. So we need to figure out what distribution it has. Well, we know it started with the chi-square with 2k minus 2 degrees of freedom, but we estimated k minus 1 of the parameters. Remember, we estimated P11, P21 up to Pk minus 1. And so we have to subtract these degrees of freedom because we used an estimate for them. Hence, this is a chi-square distribution with k minus 1 degrees of freedom. So we're going to do some examples to show you how is this used in practice. And what are the null hypotheses like, and what are the conclusions? It's a little bit funky, so let's take a look. So we took random samples of people ages 15 to 24 and 25 to 34, and we asked them about their preferred method of communication with friends. And the options were cell phone, instant message, email, other. And here are the results from that survey. Obviously, this was a little while ago because instant message was still a thing then. But you can probably interpret that as text message. Okay. So the main data is in this box that I'm putting in red. The outside data are some row and column totals. And we want to test at the 0.5 significance level whether the two populations share the same proportions of preference for each type of communication method. Okay. So our null hypothesis would be that P11 is P21, P12. P21 equals P22, P31 equals P3. P32 and P41 is P42, because there are 4 possible responses that the people could make: cell phone, instant message, email, and other. So we need to estimate these probabilities. So we need to estimate these probabilities. And so we estimate that P11 hat is going to equal 89 over 200. If I look up here, I see that 89 people report that cell phone was their preferred method out of the 200 total participants. The second one is 70 out of 200, because 70 people report that instant message was their preferred method of communication out of the 200, and the other are similarly easy to estimate. All right, so in this case, it's unique. We see that N1 is the same as N2. There were 100 people in each age group, and so what that tells me is that N1 P11 is the same as N2 P12, and that's 89. That is 100 times 89 over 200, which is 44.5. N1 P21, the same as N2 P22, which was 100 over times 70 over 200, which is 35. N1 P31 hat is the same as N2 P3 hat, which is 100 times 20 over 200, which is 10. And the last one 9.5. All right, so these are basically the expected totals. And now we're going to do a sum where we take the observed minus the expected squared over the expected. So our cube sum is 48 minus 44.5 squared over 44.5. See, where that's coming from is that 48 people in the first age group said that cell phone was their preferred method for contacting friends, and we expected it to be 44.5. The next one is 40 minus 35 squared over 35, because in the first age group, 40 people reported that instant message was their preferred method of communication to their friends, and we expected 35. And we proceed on as such. After all this, we add this up and we get a chi-square value of 9.312 with 3 degrees of freedom. So if here's my chi-square distribution, here is 9.312. This is chi-squared with 3 degrees of freedom. The p-value we can compute using RStudio. And we can do chi-square, or sorry, p chi-square of 9.312, 3 degrees of freedom, and lower dot tail equals false because we want the right tail area, and we get a p-value of 0.0254. And so this is less than alpha, so we reject our null hypothesis and accept that these populations do not share the same proportion of preferences. Now, this doesn't tell us which are the most different. It says they are different, but it doesn't necessarily tell us where they're different. Looking at the table above, we can probably guess where they are different. We see that younger people slightly prefer their cell phone and instant message to email and other means of communication whenever this survey was done, but we don't pinpoint exactly where it's done. We just say that we are relatively confident that these populations prefer different methods of communication, but we're not sure how much they differ. So you can actually do this in R very easily. So the way we do it in R is a little bit interesting. We need to create a vector of the data, but you enter it by column, not by row. So this is our data. We enter it by each column of what we've observed. Okay, and we create a matrix out of the data. And we say we have 2 rows. 1 second. There we go. So there's our matrix, and you see it appearing. And now you can just type the command chi-square.test of observed. And you get the exact same thing that we did. So this is how you'll do it in general, is you'll use Excel to calculate it from your matrix. But the first time you do it, we want you to do it by hand. So here is the command on RStudio. We enter our data by column. We create this matrix using the data entered by column until it's the number of rows. And then we do chi-square of test to get the same result that we did by hand. All right, so what's left to do? Well, the first thing I want to mention is how do we generalize this to more than just 2 experiments? It's pretty easy, and I'll just write down the key points. So generalizing to more than 2 independent multinomial distributions is relatively easy. So let's look at what the null hypothesis would be. So the null hypothesis, let's say we're going to generalize to H independent distributions. So we're going to say that these probabilities are pi. We're not sure what that is. This is for I equals 1 to k. And pi1, pi2, all the way up to pih stands for the probabilities of outcome AI occurring in these H different experiments. So we estimate pi by p hat, where we add up the observed over the total number of trials. And you might write that as the sum of the Yij over the sum of the Nj. So the Yij is the frequency of this outcome in experiment J. And the Nj equals the number of trials in experiment J. All right. So what does this tell us? This tells us that our new Q, chi-square variable Q, you just change very slightly. And it's going to look almost exactly the same as before. So this is going to be approximately chi-square, where you had H times k minus 1 minus k minus 1 probabilities that you estimated. And so this is chi-square of H minus 1 times k minus 1 degrees of freedom. And so you will do this kind of chi-square test for homogeneity on RStudio using the exact same commands as before. You'll just need to make a table that's bigger, more rows than we saw before. So the number of rows tells us the number of experiments involved, and the number of columns tells us the number of possible outcomes for each experiment. Okay, so the last thing we want to investigate is how do we handle data? that is not multinomial. For example, a continuous random variable. If I measure people's body fat index, it's not going to fall in certain categories. It's a decimal, and you will end up with as many categories as there are people at most. So how do we handle data that's continuous like that? Well, the answer is easy. Is you just create categories. It might be just ranges of data points, data values. So let's look at an example. Each of two comparable classes of 15 students responded to different methods of instruction. And they got the following test scores. So we have class U, and class V. Okay. And what we're going to do is we want to know, do these classes have equality of distribution of scores? Okay, so what we're going to do, this is a very interesting method, is we're going to divide the sample up into 3 parts. Divide the total sample into 3 parts. Basically, the low part, the middle part, and the high part. And we're going to count how many people in each class fell into each category. So how do we go about doing this? Well, it's a great time to use Excel and show you how we've do this, but we've done it before. So the first thing we do is we enter all the data values for class U. These are class U's data values. And then we enter the data for class V. And then we can just, sort based on this column. So let's look at the first group. And what do we notice? Well, we notice that there are 7 from class U and there are 3 from class V. So let's record that on the other screen. So let's create a table where we have class U, class V, low, middle, high. And here are the totals. We know there are 15 people in each class. And we see that there are 7 from class U and 3 from class V in the low scores. Now in the next group of 10, we see that there are, I think, 1, 2, 3, 4 from class U and 6 from class V. So let's record that. And then the last one's determined by it. There must be 4 here and 6 here. So now we have our table, and we can input this into our studio to get our chi-square value. Okay, so let's do that. So we insert by column 7, 3, 4, 6, 4, 6, and we create our matrix, which we call observed. And we do a chi-square test on observed, and we get a chi-square value of 2.4 with 2 degrees of freedom and a p-value of 0.3012. So we saw that our chi-square value was 2.4, the degrees of freedom was 2, and we saw that the p-value is equal to 0.3012, which is bigger than alpha. And so we're going to not reject the null hypothesis that the distribution of scores in the 2 classes is the same. Now, we haven't proved the distributions are the same. It's very difficult to actually prove 2 distributions are the same. But from this experiment, we don't have any evidence that that's the case. So we're going to just stick with the null hypothesis that the two methods of instruction produce reasonably equal scores. Obviously, there are a lot of things we haven't controlled for, but you might look at this and say, well, it looks like class V did a little better. But we don't have enough evidence. This says that the method of instruction for class V is significantly better than class U. What this test allows for is it allows for the possibility of some randomness in who's taking each class. It could be that class V had slightly stronger students, which is something this doesn't control for at all. So we're going to do some examples in class. So I hope you can appreciate the power of RStudio as we need this for more and more powerful and intricate calculations.